The Hammond postulate states that the transition state of a reaction is going to look like the species that it's closer in energy. So for example, when we have a reaction where we have our starting material here and our products here, our transition state, remember that it's this maximum right there. So what the Hammond postulate states is that my transition state right here is going to look more like the species that it's closer in energy, which in this case is the starting material, than it looks like the products that is right here. But if we have a reaction that looks like this, where we have here we have a maximum and here we have our products, our transition state right here is closer in energy to the products, and therefore is going to look like the products more than it looks like the starting material. And so that's exactly what's showing here. So we have the reactants and the products. This is endothermic reaction, and the transition state is going to look more like the products, and in here my transition state is going to look more like the reactants. So in a SN1 reaction, remember that the more substituents that we have, the more likely it is to go through an SN1 reaction. So when we get a tertiary carbocation, the reaction is more likely to happen. And why is that important? Well, because the SN1 reaction energy, the rate of an SN1 reaction increases as the stability of the carbocation increases. What does that mean? That the more stable the carbocation is, the fastest the reaction is going to occur. Let me say that one more time. So when I have a primary or methyl carbocation, the reaction is not going to happen, or it's going to happen very slowly, because that intermediate is very unstable. But when we have a tertiary carbocation, just like this one right here, the reaction is going to happen faster, because the transition state, which is the transition state that leads to the carbocation, is smaller, giving us a more stable compound, such as this carbocation. So in an endothermic reaction, the transition state is going to look more like the products and less like the reactants. So anything that will stabilize my products will stabilize my transition state. So let's look at this example right here. So if I have my products right there, so if my product becomes more stable, that will stabilize my starting material. Like here, if my product becomes more stable, that will stabilize my transition state. That is not the case for exothermic reactions, because in an exothermic reaction, the activation energy is unaffected no matter what you do to the products. So even if you modify the products, if you modify the energy of the products, the activation energy is going to stay the same or very similar for exothermic reactions. So what does that mean in terms of SN1 reaction? So in an SN1 reaction, the rate determining step, we've said this before. In an SN1 reaction, the rate determining step is the formation of that carbocation. So if we have a tertiary alkyl halide, such as this one, that will lead to a more stable carbocation, this reaction will happen faster. And when we have a secondary carbocation, such as this one, the reaction will be slower, because that secondary carbocation is more unstable. And so the Hammond postulate can be applied for an SN1 reaction. So here we start with the same starting materials, but we're going to go to a more stable carbocation or a less stable carbocation. Because when we go to a more stable carbocation, such as this one, the activation energy is smaller, and therefore the reaction is going to happen faster. That if we end up in a more unstable carbocation, such as the secondary, where we have to have a higher activation energy, and that will lead into a slower reaction. So the lower the activation energy, the faster and the more stable carbocation. The higher the activation energy, the slower, and then that will give us a more unstable carbocation.